chromatography. So what's actually going on here? How can you separate all those different inks with just a bit of paper and a solvent? Well, it all comes down to a simple race between the different dyes. I want you to think about a black felt tip pen. It looks like it's just one color, right? Black. But is it really? See, it's often a mixture of lots of different color dyes, and chromatography is the perfect technique to separate them and find out what that pen is really made of. Now, the first thing you've got to get straight in your head is that chromatography is a physical process, not a chemical reaction. Nothing new is being made. It works by separating substances based on how they play between two key things, the stationary phase and the mobile phase. So the stationary phase is the part that, you guessed it, stays stationary. It doesn't move. In this practical, it's just the chromatography paper. And the mobile phase? Well, that's the bit that does move. It's your solvent, which is usually just water. The whole separation happens because there's this competition for the dyes between the paper and the water. The more soluble a dye is in the solvent, and the less it's attracted to the paper, the faster and further it's going to travel up that paper. But dyes that are less soluble or are more attracted to the paper, well, they'll move much more slowly and they won't get nearly as far. Let's look at the practical steps you'll need to follow. Okay, listen up because this is a classic exam trap. You must draw your starting line. We call it the origin in pencil. If you use a pen, the ink from your line will separate too, and it'll just completely ruin your experiment. A pencil works because it's made of graphite, and graphite is insoluble, so it won't go anywhere. The solvent level must be below your pencil line. If it's not, your ink spot will just dissolve into the pool of solvent at the bottom instead of traveling up the paper. And in step 6, it is so important to mark the solvent front. That's the highest point the solvent gets to, because you're going to need that for your calculations later. So, the experiment's done, and you've got this piece of paper with a really cool pattern of colored spots. This is what we call a chromatogram. Now, let's see how we can turn these spots into some really useful data. Okay, so interpreting a chromatogram starts off pretty simple. If your ink separates into a bunch of different spots, it's a mixture. If it just stays as one single spot, then it's a pure substance. But to figure out exactly what those substances are, we need to calculate something called the RF value, or retardation factor. This value is basically a unique chemical fingerprint for a substance in a specific solvent under the same conditions. And because the solvent front always travels further than any of the spots, your RF value will always be less than 1. So if you get a number bigger than 1, you know you've made a mistake. By calculating this value, you can then compare it to tables of known RF values and identify your substance. Knowing the method is only half the battle. You also need to know about the common slip-ups that can cost you precious marks. You know, examiners see the same old mistakes crop up year after year. Let's make sure you can explain why they're wrong and, more importantly, how to avoid them. So, to recap the absolute key points for any exam questions on method, always use a pencil for the start line, make sure the solvent is below this line, and use a lid to stop the solvent evaporating. Getting these steps right is what makes it a valid experiment, which just means you'll get results you can trust to calculate an accurate RF value. Okay, let's wrap this up with a quick summary of the most important takeaways from this explainer. Here it is, your revision checklist. Just remember, it's all a race between the mobile phase, which is the solvent, and the stationary phase, the paper. The key controls are a pencil line below the solvent and a lid on top of the beaker. A mixture gives you multiple spots, a pure substance gives you one. And crucially, you can calculate that RF value to identify exactly what a substance is. You know, the principles of chromatography are vital in so many real-world situations. We're talking everything from analyzing the dyes they use in your food to identifying substances in forensic science and even testing athletes for banned drugs. It is such a powerful technique for separating and identifying things. Now you've got the skills. What mixtures out there are you tempted to investigate?